Hello. Let's see. You should see the desktop now, do you? And I have my speaker turned off. That was wrong. Okay. Now, I had my speaker turned off. Can you hear me?
Yes, sir.
Oh, okay, great. Thanks. Okay. I'm trying to get everything set up. I got the chat up now. Okay, let's see. One more window I need. Okay. All right. All right. So we're going to, I hope today, finish talking about the GUI aspect of the render. And on Thursday, we should start talking about the next render, which improves clipping. Because we saw a few days ago, we'll show it again, that the clipping algorithm has a problem. You know, the clipping algorithm has a bit of a problem with it. So let me see. Now let me download this and this. I hope to have a homework assignment up, a programming assignment up before the end of the week also. And I also have to let's see. Let me get this stuff open. Okay. So, you know, hopefully there'll be another homework assignment up maybe by Thursday. And then the other important thing is the syllabus says there would be an exam on the 20th, right? Okay, so that's 2 weeks from today. I'm hoping I mean, it may have to postpone it a week because I'm trying to get review material put together about what we've done so far. It'll be about the first 3 or 4 renders. The next render is going to be color. Okay, so it's going to be, the exam's supposed to be up to the first 3 or 4 renders, hopefully up through color, because that involves something called interpolation. So I'm putting together the review material, so I might postpone it like to that Thursday, maybe. I don't know. If let's see. That Thursday might be okay. If anybody has any real issue, let me know. Like if I changed it from 20th to either that Thursday, that Tuesday, or that Thursday, you know, just to give us a little bit more time to cover a little bit more material before the exam. And I just had an exam in the Java, the CS123 class. And the way I did it, it worked, was not to take the exam during class. After class, I just made the exam available on Brightspace so people could download it. You did I expected people to do the exam at home and then turn it in by midnight. So I just let people do it whenever they had time after class. So I thought it worked for that class. You know, you know, so we went ahead and had class like usual. In fact, for that class we spent the whole class doing review problems. And then when the class was over, the exam was essentially released by Brightspace. Brightspace made it available for downloading, and then it was due back up there by midnight. So I was thinking of doing the same thing for this class, and hopefully that gives everybody some flexibility. You know, you can sit and do the exam anytime in that afternoon or evening. Okay, so that's my idea for the exam. You know, not this week or next week, either this week or this week. And if you have any questions about that, let me know. Okay, but that's my plan right now. Okay, so probably not that 2 weeks from today, because I want to make sure there's enough. I want to cover a little bit more material and then make sure you have time to do the review problems. Okay, so we want to finish talking about the clipping stuff. Okay, so let's see. So hopefully a homework assignment. The homework assignment will be about event-driven programming, like what we're talking about. It'll be about using events, and then so that should be up soon. And then there'll be review problems for the exam up soon. Okay, excuse me. Anybody got any question about what I just about this stuff so far? Any questions at all so far? Okay. Um, okay, this is the render that does event-driven stuff. And this folder here tries to explain GUIs. So let's go back to this folder here that explains GUIs. Right, I'm really doing well, GUIs is not important to the graphics class. So some people who teach graphics class don't even mention the word GUI anywhere because graphics class is about filling a frame buffer. Yeah, that's what a graphics is like. How do you fill a frame buffer with a 3D scene? Making it interactive, some people cover that in their graphics class, some people never touch it in their graphics class because it's kind of it's there's a limit to how much you can cover in one class. Okay, so I'm trying to do a little bit of introduction to GUI, but GUI programming is actually usually considered its own topic. Yeah, so some schools have a course in GUI programming, but almost nobody teaches it as a course anymore. But there's lots of books and lots of seminars and online courses that teach GUI programming. It's if you need it for a job, it's real important. But if you don't need it, it's one of those things where it's not ubiquitous like data structures and algorithms that are running through everything in computer graphics. GUI programming is just something you're going to do if you're going to do front end development, and even if it's what people mean front end development is usually web page design, which is related to GUI design because it's a GUI, but it's kind of different than this GUI design. What this kind of GUI design is mostly applicable to if you're going to write Windows desktop applications, and a little bit if you're going to write cell phone apps. They have a little bit of GUI-ness combined with a little bit of web applications mixed in. Okay, but writing if you were to end up working for someone where you write real desktop apps like text editors, you know, like this is heavy duty GUI programming. Okay, that's what this is all GUI programming here. Okay, all right. So so let's talk about GUI programming. But then over here, this was to use just enough GUI programming to make the render interactive. So what's going over here is just a tiny amount of GUI programming just to make the render interactive. Okay, so this is a lot more GUI programming that's needed over here. Okay, so we're going to talk a lot more about just because I think it's a good place. It's as good a place as any in your years here at school to see some GUI programming. So this is more than we need over here, but it's a good thing to do. What we need over here is mostly events. Okay, now here's the outline we have. Okay, GUI programming really boils down to knowing about 5 topics. Okay, there's these 5 topics. These 3, that's what we talked a little bit about the other day. We covered those 3. That is the visual part of the GUI. Okay, making it show up on the desktop and giving it a certain appearance, the components, the containers, and the layouts. Then this is the event part, making things happen. Making something happen when you click on a button, making something happen when you use a slider. From the point of view of the render, we don't need any of this. Actually, we need one of these. We need the J panel. That's it. We need only one, and it's not even a component, it's a container. So we need none of the components, and we need one container, that's the J panel. That's the only thing the renderer needs. But the renderer uses a lot of events so that you can do things like eventually mouse clicks, keyboard clicks, resizing the window. We'll see that resizing the window is actually a special kind of event. Dealing with this, resizing a window is is an event. Okay, so the render actually uses a lot of events, and it uses one container to hold the frame buffer. It uses a J panel to hold the frame buffer, and that's it. Okay, but over here, I want to talk about more. We're going to keep talking about just traditional kind of Java GUI programming with buttons and checkboxes and JText fields. Okay, so here's the idea: is that you have components, Those are the things that your user interacts with. You can see label, button, checkbox, combo box, list, text field, text area, scroll bar, radio buttons, sliders, scroll panes. These are the things that, like, if you look over here, you can kind of see where they, let's see. Well, menus. Menus are components. This is actually, I opened Notepad. So Notepad's not such an interesting GUI. If I open TextPad, like we saw the other day, there's a lot more areas. See, there's buttons and text fields and checkboxes. Okay, so so label would be like that. That's a label, match case. Checkbox, that's a checkbox there. There's these little arrows, but they're not in this list. This list is just a subset of the basics. That right there would be a text field, okay? These are all buttons, but they're buttons organized into a toolbar, okay? So a toolbar is just something that lets you organize a bunch of buttons as a unit, okay? This is a tab. I don't know if, yeah, see, that's a tabbed pane, okay? So I can open up another tab, those are tabbed. This is a tabbed pane. Now I'm using Java terminology, but this is a Windows program. Windows doesn't call these things, but they usually have their own names for all these things. So I'm referring to them by their Java name, but there's probably no reason to think that Windows uses those same names. Then there's stuff like what's over here, which wouldn't even be in this list of basic stuff. Well, this is a list. Like that's some kind of list. An interesting thing is like this, where you get this drop-down list that lets you change between different things to show here. I have no idea what this is called. Like this is some kind of component over here. See, it's got this little drop-down list. You change you change the list that's showing in the drop-down list lets you choose what list to show down here, and then that window can be closed or reopened. I mean, this is some kind of component in the Windows library, a pretty useful kind of component in the Windows library. Okay, all right. So you've got components are the things your users interact with. You've got to organize them. So you need containers to hold them in, okay? You organize, now you don't really need, the idea is you could just open a big window and start plopping components in it. That's not how it's done. You don't open a big window and plop a button here and a button here and a button here and a button here. They're built up in a hierarchical way. So you have a big container like this window, and then it'll be chopped up into smaller regions, and each region will be a container. So this window might be 5 or 6 containers. Like this region up here is probably a container by itself. This region here is probably a container by itself. And this guy here is probably some kind of container. And then you put things in the containers. So, and then the containers can hold containers within them. Like this container here probably has 2 or 3 toolbars in it. Like that's at least one toolbar. That's either a toolbar or a menu bar. Okay, but those would be 2 more containers sitting inside of maybe this container. Okay, so you organize the components in the containers. The containers, like over here, Java has only really 4 kinds of containers: JPanel, window, frame, and dialog. These are considered top-level containers. They float around the desktop. That's something that floats around in the desktop. This is a nested container. You put this guy inside of any one of those 3. Okay, so you have 3 kinds of, like this is meant for dialog boxes. Things like, see, that's a window that floats by itself, but it's not an independent window. That's not a program. So that kind of window, it's top-level window, but it needs it's a special kind of top window. In Java land, it's called a dialog. Okay, so that's a top-level window because it can float around by itself. You put things inside. See, here it's full of checkboxes and tree views. Okay, but it only can live, like if I close TextPad, this thing will close with it. I don't know if I can. Now this one's called Modal. See, this dialog box is what we call modal. I cannot do anything back here. Okay, this modal dialog is blocking everything behind it. And in Java, when you create a dialog, you can make it modal or not modal. When you make it modal, it's in the front and it blocks everything behind it. I don't know where the word modal, I never could figure out where the word modal came from. Okay, but that's what this is referred to as a modal dialog box. Okay, so that's a top level window. It holds containers inside of it. Okay, so Java has a dialog. I don't know why they have two different. Oh, this is the top level window you use. That's this. This is a frame. If I remember right, this is a window with nothing around it, like you might use for certain kinds of games and stuff like that. When you create a window, you don't get the title bar at the top. You don't get these little buttons. If I remember right, you don't get these little buttons. It's like a bare bones window. And I don't know what Windows doesn't call the, I don't know what Windows uses for these phrases, but this frame is the usual window that like you're used to here. And this is kind of a special case window that would be used for programs that have like, I guess maybe a real bare bones GUI. Okay. So you don't use them very often in Java. Like in Windows terminology, I don't know how, like what they call these two different kinds of windows, but this is the regular one, the one that has what we call the decorations, a title bar, a minimize button, a maximize button, a close button, a little thing down here that you can grab to resize it with. Okay, those features are part of a J frame, and they're not there in a J window. Okay, so dialogues are special. They're for pop-up windows. These are you have two kinds of desktop containers, top level containers, and then this is the workhorse. Everything else is put in a J panel. So you'd fill this up with J panels, and you fill J panels up with J panels. Usually you put J panels inside of J panels inside of J panels, and you put all those inside of a J frame. Okay, so components are packed into usually panels, and then panels are packed into J frames. Okay, now how things sit inside their container. Okay, if you put 3 buttons in a panel, how do they sit there? That's what the layout managers do. They lay out the components in the containers. Okay, so they lay out the components in the containers. Okay, and they do it for you automatically. The idea here is this is a convenience. Like some people asked last week, could you just put components exactly where you want them? And the answer is yes, but usually you don't want to be putting components pixel by pixel by pixel. So it's usually just a lot easier to let them be laid out automatically by some strategy. And we saw border layout gives you a north, south, east, and west region and a center region between. Flow layout acts like text. Everything is next to each other until you run out of space, and then the components flow to the next line, and they're next to each other until you run out of space. Then the components flow to the next line. Okay, grid layout and car layout stack the components like in rows and columns. These three are various kinds of rows and column layouts. Okay, so they don't let you put components exactly where. Oh, well, if you want to put the components exactly where you want them pixel by pixel, then you don't use a layout manager. You don't have to have a layout manager. So every container has a default layout manager. You can change the layout manager and you can remove it. And if you remove it, then it's up to you to put everything pixel by pixel in the right place. You have to put everything, and then you have to worry about where should things go when the window resizes. That's the hard part. That's why people use automatic layout managers. It's not so hard to put things in where you want them. The hard part is to rearrange them when somebody does this. Now you can make your windows not resizable. You can turn off the resizing, and if you do that, then they might lay things out pixel by pixel because they don't have to worry about anything resizing. But boy, is it a nuisance to deal with this. Okay, you could just assume your everything chops off. You could, like here, notice a lot of things are just chopping off. If you see here on the left, a lot of things are just chopping off, but not everything chops off. Like this menu bar here, it flows. See, that menu bar flows. The toolbar below it chops off. The toolbar chops off, the menu bar flows. Oh, but the toolbar doesn't, notice how okay, look how weird this is. I'm not sure if they really meant this. This guy chops off, this guy stays there, and these chop off. Isn't it? It's kind of weird. See, first the match case button chopped off, then the text box stays there and just keeps scrunching the toolbar smaller and smaller and smaller. Okay, all right, so that's their layout manager. Their layout manager is deciding to do that. Okay, all right. So sometimes the layout managers, that for some reason, maybe this box is so important they don't want it to be chopped off, but they don't care about this and they don't care about those buttons. And they chose not to make those buttons flow like the menu, like the menu bar usually flows, because the menus, you don't want them disappearing. So a lot of programs make the menu bar flow, but a lot of them make the toolbars flow also. I've seen toolbars that'll flow to another line too. Okay, all right. So, so these three things are your appearance. The components sitting in containers laid out for you automatically by some strategy in the layout manager. Okay. Now the harder part, all this is kind of hard. Designing a very elaborate GUI like this takes a huge amount of work. Okay, but we're not going to do elaborate GUIs, but we're going to do kind of elaborate events. Okay, so for us, the events are going to be the more detailed thing. Okay, events you have what are called event objects and listener objects. Now, to talk about that, this just gives you the names of all the events and the names of the listener. Oh, each event has a listener for it. So notice that there's 8 items in this list and there's 8 items in this list. So action events have action listeners. Item events have item listeners. Text events have text listeners. Okay, the idea is that each kind of component can generate certain kinds of events. Okay, so a button doesn't generate a text event, because a text event comes from something you can type into. A button usually, I can't remember if it's an item event or an action event or both. Okay, button I think is maybe action event or item event. Okay, now a scroll bar is an adjustment event, because you adjust a scroll bar, you slide it. So a scroll bar gives you an adjustment event. Text fields and text areas generate text events. Okay, now these events are called high-level events, and these are called low-level events. We'll see the difference. The low-level events actually come from, everybody generates the low-level events. So all components generate low-level events. The high-level events are tied to particular components. Okay, so not everything can generate an action event. Only certain of these can generate action events. Certain of them generate item events. Okay, everything generates mouse events. Okay, oh well, window events come from containers. Okay, so window events come from containers. Key events and mouse events can come from anything, and focus events can come from anything. Okay, so these can come from any component or any container. These come from containers only, and these come from various components. Each one comes from certain components. Okay, all right. Now, the idea is that when somebody clicks on a button, there is that creates a, say, action event, which is given to an action listener. And then the action listener does what the button wants done. So let's look at code. This is the tricky part, because this brings up a whole new thing called event-driven programming or interrupt-driven programming. Okay, so now let's turn to some code examples. Okay. Let's see. I want to start with, I think it's this one. So let me compile this, run it. Okay, there's the GUI. Okay, and the GUI's just got one big, oh, I'm sorry, this is not the one I want to run. This one's got a timer in it. So do the one before it. think it's this one. No. Okay. Dumb GUI with one component in it. Okay. So the component is just a big fat button filling up the whole window. Okay. And you click on it and you get this ouch over here. Okay. So now let's trace through this code real carefully. Okay. Here's the code. There's the output. And there's the GUI. Okay. So I start by creating a JFrame object that creates this top level window. Doesn't make it show. It's only an object in the heap at this point. Okay. Then I create a button object. Again, at this point, it's just an object in the heap. Okay. Then I create a action handler object. Okay. Now notice it's called. Okay. So I create this object down here. Okay. So this is the object. This is the class. So I create an instance of this class. Okay. This is the action listener. The action listener is an object. Well, an instance of this class is the action listener. So I create this object. I call it callback. Okay. And it's got the code in it that handles what to do when you click on this button. So when I click on this button, this is the code that runs when I click on this button. But how does Java know that I want this code to run when I click on this button? Well, I create the object that holds the code. Okay, so I create an instance of the object whose, you'll notice it's only got one single method. That method is the action performed method. The thing to do, what do I perform when there's an action event? What do I do when an action event happens? Okay, see, here's the action event. So what do I do when an action event happens? Okay, so I create an object that holds that code. I'm not calling that code. I'm creating an object that holds that code. Then I tell the button that this is the code that you should pay attention to, that you should call when an event happens. Okay, so the button, I add action listener. Okay, this object is added to the button as an object listener. Okay, then I add the button to the window, but the window's still not visible. I set the window size to 400, 400. Then I make the window visible. Okay, then the window pops up here. Then I print by, and my code ends. Notice that the main method, see, I was in the main method. The main method ends. Now, normally, when the main method ends, what happens to a program when it gets to the end of the main method?
Exit.
Exit. But my program's not exited. It's running. And that's one of the things we want to talk about is like, how do programs run after they've exited? What does it mean to talk about exiting a program? What's going on here? Yeah. Now, so like here's what I mean by that. Here's a program called Simple Program. This is what you're used to. This is a hello world. Okay. You compile this program and you run it, and it prints by and it ends, because when you run it, the Java virtual machine calls your main method. You do everything in the main method. You get to the end of the main method, and the program's done. So the program terminated. Okay. But notice that that's not what's happening in the GUI program. When you get to the end of the main method, see it printed by's up here. You get to here, the main method's done, but the program's still running. Okay. And we need to talk about why is the program still running if the main method is terminated. Okay. For example, what's my program doing right now? I mean, it's a real interesting question is what's happening right now? Now, if I click this button, I get ouch on the left. Every time I click this button, this runs. Okay, so see, there's the line of code to put that over there. So every time I click the button, that line of code is executed. but like what line of code is being executed right now? Okay, so let's look at another picture to try to understand this. In the render 2 folder, there's this README, and it's got an explanation of event-driven programming, not GUI programming. In here is a description of event-driven programming. Okay, so event handling. Okay, event-driven programming is a pattern of programming that, if you learn it in Java, you've learned it everywhere. You know, Python, JavaScript, everybody does event-driven programming the same way. So one language is a good way, any language is a good way to learn the idea of event-driven programming. Here's a picture of event-driven programming. Okay. In this picture, here's how it works. You have a GUI object. That's this button. The GUI object can generate, it can create events. Things like you can click on it, you can check a button on it, you could toggle something on it. Okay, so you have a GUI object. I should have used the word, well, I used the word object because this is a picture of the heap. So this is the GUI object representing some GUI component. Okay, but this is a picture of objects in the heap. Okay, so this button is an object in the heap. Remember, we said that when you, at this point, you've got a object in the heap. That's the button object. Okay, so there's the button object in the heap. Okay, the button object in the heap has a list in it. Every GUI component has a list of what are called its event listeners. Okay, now notice over here that I added to the button this thing here. See, add action listener is adding to this list. Okay, so that method called put an object in the list. What it put in the list was an event listener object. See, I created an event listener object. It's an event listener object because it implements, it says here, implements action listener. And I called it callback. I'll say why I called it callback. I gave it the name callback, and I added that, a reference to that item into that list. So in this picture, here's the event listener object. Here's the list inside the button object, and the button object is pointing at this event listener. Okay. All right. So that's created by these 3 lines of code. Create the button, create the event listener object, add the event listener object to the button. So that created this object, and put this object in that list. Okay. What you're eventually saying is, this holds the logic of what to do when you interact with this item over here. So when somebody clicks on that button, this is what code should be run. It handles the event. Okay, or it listens for events. Different people have different ways of, Windows calls them handlers, Java calls them listeners. Yeah, so I use both words here. Windows calls them event handlers, Java calls them event listeners. They are listening for something to happen. When something happens, they handle it. So it depends on what you want, your point of view. It's listening, and then actually, it turns out that handles a better name for it. It handles the event. Saying it listens for the event is actually misleading. These things don't listen. So Java, I think didn't really choose the right word here. I'll show you who listens. So Java calls them listeners, but they actually aren't doing the listening, but they definitely are doing the handling. When an event happens, this is the code that's running. Okay, so now let's take this button over here. Who's listening for something to happen to this button? Okay, now to make something happen on that button, like here's my mouse is down here and I'm clicking the mouse. It has nothing to do with the button. Right now, the mouse is over the button. At this point, if I click the mouse, then I've activated the button. Think about it. Who is really listening to whether I'm clicking on that button? Anyway, who is it? I'll give you a hint. Operating systems class.
What's the question?
Who is listening to me being about to click on that button? Who notices that I clicked on that button?
Explorer.
Even more abstractly than that. Explorer, no, actually the answer is not Explorer. Because Explorer is an application level program. Who knows that I've clicked the button, that I've clicked the mouse?
Your mouse driver.
Okay, the mouse driver. Who's that part of?
Operating system.
The operating system. Yeah, the driver is part of the operating system. It's the mouse driver, part of the operating system, that's listening to the mouse. They're listening to this. Okay. This object does not listen to the mouse. It can't, because it's a user level program. Remember from operating system, all hardware devices like the mouse, the screen, and the keyboard are owned by the operating system code. Okay, so when I click over here, it was the operating system that said, oh, the mouse button interrupt happened. The mouse driver notices the mouse button was clicked. The mouse driver informed the operating system that the mouse button it clicked. Okay, then here's what happens. The mouse driver sees that click. The mouse driver informs the operating system about the mouse click and the pixel location on the desktop where the mouse clicked. The operating system has a picture like this saying, who cares about that mouse click? So the operating system says, you know, the mouse just clicked. Like down here, nobody cared. Up here, somebody cared. So the operating system, now can you see, what did the operating system notice between here and here? What did the operating system look for?
Talking about the pixel coordinates?
Well, the mouse was clicked, and the mouse driver said, I got clicked at this pixel location. And it gives that information to the operating system. What might the operating system do at that point? Like, I'm clicking here, I'm clicking here. Right. What does the operating system notice about down here versus up here?
That one isn't the button and one is the button.
Well, one, like here, I'm clicking. What is the operating system going to notice when I click in here?
That you're in that window.
Yes, that you're in that window. So if the operating system sees that the event was in this window, who does the operating system then communicate with?
That application program?
Right. That process, TextPad process. When the operating system, now what happens when the operating system sees these mouse clicks down here?
Nothing.
Why?
Because it's just the background window to your computer process?
Yeah, well, it actually probably at this point talks to Explorer and says, you know, is there anything there on the desktop? And the answer, like here, there's something on the desktop. See? So those mouse clicks opened my trash. These mouse clicks, they were probably passed to Explorer, and Explorer said, not you know, I don't care. So the mouse clicks were probably passed to Explorer, and Explorer said, I don't care. But the mouse clicks here were passed to Explorer, and Explorer said, ooh, let me open the trash can. Okay. Now here, the operating system sees that these mouse clicks are over a window owned by who? This is a tricky question. Who owns that window?
Java.
What do you mean Java?
The Java program. That,
what's it called? The hardcore technical. You know, you want to be able to give the you want to nail the answers in these technical interviews. Who?
JDK.
No, it's
JVM,
pardon me.
JVM.
JVM, the Java Virtual Machine. That is the Java program. See, if I call up Task Manager, here's my Task Manager, go to Details. The Java program is the Java Virtual Machine. This guy here. Okay, that's the JVM, the Java Virtual Machine. Notice it's not my Java program that owns this window. It's actually the Java Virtual Machine. So when Windows sees me click here, Windows says, there's a Windows operating system. When I click here, the operating system says, the mouse click happened in a window owned by the Java Virtual Machine. A window opened by this process here, 8116, okay? So the Windows operating system sends a message to the Java Virtual Machine saying, you've got a mouse click and this pixel in your window. Now, what do you think the Java Virtual Machine wants to do with that?
Print ouch.
What?
Print
No,
ouch.
eventually, we want to do all the steps very carefully. We're walking our way logically and carefully through the steps. So
Handle event.
Pardon me?
Handle event.
Yeah, but how? Yeah, okay, so let's start back at the beginning. I click the mouse driver sees the mouse click. The mouse driver is part of the operating system. It informs the operating system of a mouse click at a certain spot on the desktop. The operating system sees who owns that pixel on the desktop. Is it Explorer? Is it TextPad? Is it the Java Virtual Machine? It sees that it's the Java Virtual Machine that owned that pixel. So it sent a message to the Java Virtual Machine saying you had an event on that pixel. Okay, the Java Virtual Machine wants to do what with that event on that pixel?
Pass it as an argument.
To who? See, notice we're talking about who's passing it to who. What?
To the event listener object.
No, well.
I mean.
Well, to who? Yeah.
The handle event method.
In my program, yeah, it wants to. This is where it wants to. Now the Java Virtual Machine wants to call that handle event program. Okay, so the operating system sees the mouse click. The driver sees the mouse click. The driver informs the operating system. The operating system notices where it is on the desktop and says, oh, that's a window owned by the Java Virtual Machine. The operating system says to the Java Virtual Machine, you got an event. The Java Virtual Machine says, who owns that pixel in my window? And it says, well, it's this guy's program. It's this program here. So the Java Virtual Machine says it's this program that needs the event, and it sends the event to this method here. This is the message that finally flows to my code. It started where? This message, where did it start?
The callback.
Where did it start? The message, yeah. Where did the message originate from?
The mouse click.
Yeah, the mouse click. The mouse driver, remember, mouse driver sends a message to the OS. The OS sends a message to the Java Virtual Machine. The Java Virtual Machine says, who of all my Java processes owns that pixel? And then it calls this. Now, how does it know to call this? Okay, that's this picture over here. When the Java Virtual Machine gets the message from the OS, the Java Virtual Machine creates an event object in the heap. Okay, so the operating system sends some kind of message to the Java Virtual Machine. I actually don't have a clue how that's done. Okay, that part is below what we need to worry about. Okay, but the operating system sends some kind of message to the Java Virtual Machine. The Java Virtual Machine gets that message from the OS and it bundles it in an event object. That event object has information like what pixel was clicked on, at what time was the click, was it a left mouse button, a right mouse button, all kinds of information about the mouse click is bundled into this object. Remember, objects are data. Okay, so the Java virtual machine collects a bunch of information from the operating system and bundles it into an event object. That's that. So when the Java virtual machine gets the message from the operating system that there's been a click, it creates this event object. Then it wants to know who to send it to. Okay. The part of this, like, if I had more than one button here, in this event, it would know which button it came from. So the Java virtual machine actually knows what component you clicked on. So it knows if you clicked on button 1 or button 2 or button 3. So suppose you clicked on button 1. The Java virtual machine goes to that button object, goes to this list of listeners, but they're really not listeners, they're handlers, and says, okay, I need to call the code in each one of these handlers. So it actually steps through this list, and we'll see in a minute, you could have more than one handler. So it says, okay, I'm going to call that object, I'm going to call that code, and I'm going to call that code. And each one of those codes gets a copy of this event. Oh, see, this event E is this guy here. This is the event object. So this E is this object here. It was created by the Java virtual machine using the information from the operating system. Okay, so the Java virtual machine builds that object. It knows which component this object really came from. You know, it knows which one of my components the mouse was clicked on. So it goes to that component, looks in its list of event listeners, and starts calling the event listeners. Okay, so over here, here's where I put into the list of event listeners my code, which is an instance of this class. Okay, all right, and then when this code is done, I've got this picture. I created, this is the button object. This is the event object that's created when I click a button. And this is that one event handler object. Okay, so the button object, the event handler object sitting in a list in the button object. This code is sitting in the heap, just sitting there. Okay, and then actually, my program ends at this point. Now, let's go back to that question. If my program ended, what's running? Well, what's running is what's called the event dispatch thread. When you create a GUI, you create something, by default, you create something called the event dispatch thread. The event dispatch thread is the thread the operating system passes this information to. It's the thread that gets these events from the operating system and calls these methods for you. Okay, so this process of building an event object, going up here to this list, finding these methods here and calling these methods here, that's done by the event dispatch thread, not by your main thread. Okay, now the event dispatch thread is created when you create a GUI. I'll show you. Okay, let's see where that comes from. Okay, so close this program. Let's look at another program. Go one step back. Go to Simple GUI Program 1. Oops. Create a frame. Create a button. Give the button a listener. Add the listener to the button. Add the button to the frame. Set the size of the frame. Say goodbye. Run this program. What happened to the GUI? Notice my program.
You didn't say, you didn't call set visible?
Yeah, the set visible is the thing that triggers that event dispatch thread. Since I never made the GUI visible, that extra thread never got created. Okay, so now here's version 2. See, the only difference between version 1 and version 2 is version 2 adds this make the GUI visible. that starts the event dispatch thread. Once the event dispatch thread has been started, it doesn't matter if my main thread dies, there's a thread running in the Java virtual machine that keeps my program alive. The thing that's interesting is that this code runs on the event dispatch thread, not my main thread. So it's actually running on a different thread, okay?
What
So,
exactly is a thread?
think of it as there's two CPUs. One CPU is running this and one CPU is running this. It's kind of hard to explain what a thread is. It's in the operating systems class, we talked about what a process is. A process is the process control block that maintains the state of a CPU that's executing the code in the process. A thread is just a thread control block. It's processes living inside of a process. A thread is a process, a thread of, we call, it's a thread control block. It's a state of the CPU living inside of a process. What that means is, if you draw a picture, it looks kind of like this. I don't know if I can draw a quick picture. In the operating systems class last year, we kept drawing a picture. There was one picture we kept drawing over and over again. This is the CPU, and this is the virtual memory. And inside the CPU is a program counter. I lost my, oh, there. There's a program counter in here. Okay, and the program counter tells you where the CPU is executing in memory. So the program counter, would be at any given time, the program counter be pointing at some address in memory. That's where you're executing, right? Okay. And then you could have two processes. So you could have a second process. So you could have a second virtual machine over here. It represents a second process. So this would be virtual machine. This would be another virtual memory map. There's another virtual memory map. How do you run two programs at the same time? If you only have one CPU, can you do that? Can you have one CPU run two programs?
Context switch.
I'm sure.
Time sharing context switches. Okay, time sharing context switch. But the way you did that was you had to have two process control blocks. So there was a data structure over here called a process control block, and another data structure over here called a process control block. So if this is virtual machine, this is virtual memory 1, this is virtual memory 2, this is process control block 1, and process control block 2. What do they got to do with this? I want my one CPU to run two programs simultaneously.
It saves the state of the program when it switches.
When you want to stop running this one and switch over to this one, you have to take everything in this CPU, put it over there to save it, take everything out of here, put it in the CPU, and now your CPU is pointed over here. And now the CPU is running over here. What made you switch from here to here?
It ran out of time, or it's making a system call.
Made a system call over, yeah. So run out of time was that there was another little box in this picture. There was the timer that could interrupt the CPU. Remember? Now that timer interrupt is exactly where events come from. if you really want to know like what really starts an event, over here I can put another little box in this picture. Here's a box with another kind of interrupt. Mouse. When I click the mouse informs the CPU that there's an interrupt. Just like the timer, you know, the timer would interrupt the CPU, say it's time to go from here to here. Then when the timer interrupts it again, it's time to jump from here back to here. Well, when the mouse clicks, the mouse interrupts the CPU. And it causes a trap to a particular, causes a trap from user mode to kernel mode. Remember, so you trap, these things cause traps from user mode to kernel mode. Okay, now this is processes. What are threads? Okay, here's what we do. We add for this process control block, I put down here 2 thread control blocks. Okay, and for this process control block, well, okay, so this is a thread control block 1, and this guy is thread control block 2. Okay, and then maybe this process control block has a couple thread control blocks also. Here's what happens now. I can think of this program, this virtual machine is holding here's the main method, and here's my interrupt handler, my event handler. So think of, you know, the code. Here's main, and then here's the handler down here. So I got 2 chunks of code. You know, over here, main is that chunk of code. Action performed is that chunk of code. I can have this thread running in main and this thread running in here. And then what that means is the single CPU is either, well, suppose the single CPU is running in here, and then the timer interrupts. What happens is instead of doing a process switch from this process to this process, I can do a thread switch from this thread to this thread. So that means that this data, the state of the CPU, doesn't go into this process control block, it goes into this thread control block. Then this thread control block is copied up into here. So now I jump from this thread to this thread in the same process. So now the CPU is running down here. Then the timer fires again. So the scheduler decides we're going to go from this thread to this thread. So this thread is stored in that thread control block. This thread control block is put into the CPU, and now you're running this thread. Then a little bit later, the timer fires again. And now the scheduler says, no, we're going to run a thread over here. So over here, there's some other thread. There's a, well, you know, this guy's got a main method also. There's a main method in here. And there's going to be a thread control block over here for that main method. So there's a thread control block over here. This would be thread number 3. It belongs to that process, but this would actually be thread number, this is be, from the point of view of the operating system, this is our 3rd thread. So this is thread control block 3, but it belongs to process 2. So maybe I should like put a little arrow saying this thread belongs to, this thread is tied to that process. This thread is tied to that process. And this thread is tied to that process. So I've got 2 processes, one with 2 threads and one with 1 thread. But what the operating system now switches, when the timer happens, the operating system switches from thread 1 to thread 2 to thread 3. Now, when it switches from thread 2 to thread 3, it's switching from process 1 to process 2. That's what it is. It's a harder context switch. Notice you've now got inter-process context switches and intra-process context switches, but they're still the same idea. A thread is just a context in a process, and a process can have as many contexts as it wants now. So instead of having just one context per process, the thread control blocks are multiple contexts per process. That's what a thread is. That's actually, this is a 100% accurate description of what a thread is. This simple picture here. It's a pretty much a 100% accurate description. It's just thread control. What was in the process control block, most of it moves into the thread control blocks. All the CPU state is now kept in the thread control block. So when you switch from this thread to this thread, you switch from this thread control block to this one, you take when you're running in here, take this CPU, put it in here, store it in there, grab what's in there, put it in the CPU, you've now jumped to there, and you're running inside there. Then when the timer decides it's time to move you away from that thread, then the operating system says, well, picks a thread 1, thread 2, or thread 3. It's more work to jump from this thread to this thread than it is to jump from this thread to this thread, but that's up to the operating system. That's a detail that's not that important. The main difference is the page tables. You don't change the page tables when you swap from this thread to this thread, but when you swap from this thread to this thread, you have to change the page tables because you're in different virtual memory maps. So moving from here to here involves updating the page tables. Moving from here to here does not involve updating the page tables. So that's the main difference. Okay.
Thank you very much.
It's the main idea from operating system, just one layer deeper. You know, instead of just process control blocks, it's process control blocks and thread control blocks. We say briefly it's a thread of control. You know, it's the CPU threading its way through this code versus the CPU threading its way through this code. Oh, and what if you have two CPUs? The interesting thing is, what if there are actually two CPUs? What becomes interesting about this?
Will this just be multi-threading?
No, what I'm showing you is multi-threaded. This is multi-threaded, even with one CPU. This process has multiple threads. Okay. What if I throw another CPU into the picture? So this is just CPU 0 now, and I can add a CPU 1 if I wanted to. What makes this interesting if I add another CPU?
It can run two programs at once.
Be careful. Right now I'm running two programs at once. I'm running virtual machine. I'm running this program, and I'm running this program. I'm time slicing because I only have one CPU.
Run in parallel?
Run in parallel. If I have a second CPU, but what's real interesting here, I'm not going to run two programs at once. What's real interesting if I throw a second CPU into this?
One CPU will run one program, the other one the other program.
No, that's running two programs at once. I want something even more interesting than that.
One to listen the whole time?
Well, yeah, so what do you mean? I've got
with the handler.
So what would be the new interesting feature? Instead of running two programs simultaneously, I could be doing what?
CPU 0 could run main and CPU 1 could run the handler thread.
Right. So I could have two threads running in parallel in the same process. What's called concurrent programming, or what sometimes people mean by multi-threaded programming, except this is multi-threaded. Multi-threaded doesn't mean you have multiple CPUs. But if I have two CPUs, I could have one CPU running this thread and simultaneously have another CPU running this thread. So my program can be doing two things at once. Now, notice that traditionally, you can think of a computer as doing two things at once because you could have one process here and another process here. But now I'm switching to the idea that one process can do two things at once, because there can be a thread running in this part of the code and another thread running in this part of the code. One CPU could be running this thread and another CPU can simultaneously be running this thread. And if I've got 8 cores, I could have 8 threads all running inside of this one process. That's modern parallel programming. You could have all the CPUs running within one single process. Now, it could be you could have 5 CPUs in this process and 3 CPUs in that process. So then you're running 2 processes simultaneously, but each process has got multiple threads running simultaneously. Like my machine has got, I forget, what has my machine got? 12 cores. Not that it really has 12 cores. It's got 6 physical cores and 6 more logical cores. But essentially, it pretends to have 12 cores. So I could have 5 cores running in this process, another 5 cores running in this process, and 2 more cores left over to run some other process. Okay? But notice I would have 5 things happening simultaneously inside this process here. That could be main and a bunch of handlers all running at the same time. See? That could be, or that could, that could be the main method, an IO method, and a handler method running at the same time. So I could have one thread downloading something from the internet while another thread is updating the GUI while another thread is sorting a list. Which is what programs like Chrome do. They'll have one thread downloading something while another thread is painting a GUI while another thread is sorting things. Okay, so you have one program doing things simultaneously. Okay. Okay. So that's a real good question. I mean, it's real good to just real briefly talk about what do we mean by a thread. Okay. Okay. Now, back over here, in this picture, this does not have to be multi-threaded. This does not require multi-threading. Well, I'm sorry, it does require multi-threading, it doesn't require multiple CPUs. I'm sorry, this picture requires multiple threading, but it does not require multiple CPUs, okay? Actually, it doesn't even require multiple threading. Java does it with multiple threading, but in the old days, this was not done with multiple threading. In the old days, before, if you go back to the 70s and 80s, they had GUIs, but they weren't multi-threaded, okay? What Java chooses to do is it has one thread to run your main and one thread to run the GUI. In the old days, what they would do is they'd have one thread. And when that thread was done running main, then it would switch to running the GUI. So it would just switch. You would, instead of, see, the way it works now, in Java land, when that thread reaches here, that thread dies. The thread that starts your program and starts in main, when it gets to here, it dies. But this thing here starts the other thread. This thing launches the other thread. Then the other thread handles the events. In the old days, they would just have one thread, and that thread would first launch everything. And then after it had launched everything, then you had to make a special function call that said, okay, now switch my thread into event mode. Okay. And if you look at old Windows programs, there was a function, I can't remember the name of that function now, but it was a famous function because that was the function that took your main method and switched it to running the GUI stuff. Okay, it still stayed the same thread. There wasn't 2 threads, but after the thread was done, after you did all your setup, then you'd call this one function that basically said that now you could switch to this picture here of waiting for events from the operating system. When an event comes from the operating system, calling the event handlers. Then when the event handler returns, you go back to waiting for an event from the object. Okay, so it's the event dispatch thread that does this waiting for events to happen. When an event happens, it knows who generated the event. The operating system tells it, the operating system gives it enough information that the event dispatch thread knows whether it came from button 1 or button 2. Then it goes to the object that created the event, It goes to its list of listeners, which aren't really listeners. Again, I think Windows had a better name for them. They are handlers, not listeners, because they're not really listening. It's the operating system that's listening for events because it's the one that owns all the hardware. Okay, but Java called them listeners. Okay, so the event dispatch thread, it listens for the events. When it gets an event, it figures out who generated it. It goes to its list of handlers and it calls each handler. Okay. Okay. Now let's look at version 3 of this program. Now version 1 showed you that just building a GUI doesn't mean you have a GUI. If you don't trigger the event dispatch thread, when the program ends, everything ends. You got to somehow trigger the event dispatch thread. Okay. One way to do that, not the only way to do it, but one way to do it is to make a GUI object visible. When a GUI object becomes visible, that triggers the event dispatch thread. Here's something interesting. Trigger the event dispatch thread. Call system.exit. Anyone want to guess what that does?
Exit the thread.
Pardon me?
Exit the thread.
It might exit the thread. See, it's actually not clear. Okay, now system.exit. Does that exit the thread? Well, if it exited the thread, we know that if you exit this thread, the GUI stays running, right? But what else might it do?
Stop the process, maybe?
It might exit the whole process. Okay, it might exit the whole process. Let's find out. Do you see the GUI flash? That
Yeah.
it exited the whole process. The GUI got started, and then before the GUI got very far at all, I exited the process. Okay, so system.exit exits the process, not the thread. That's important. Like,
Is there a way to just exit the thread instead of
well,
the
the
whole
best
process?
way to exit the thread is just to exit the main method.
Oh, okay.
Yeah, see, yeah. Now there is a method for exiting a thread, but I don't. That's return. Yeah. So, for example, return means exit the thread. Now Java won't let me do this because the Java compiler is real smart. See the error message? What did the Java compiler notice?
You'll never reach code after you return.
Right, so the compiler says, this is idiotic. Why are you doing this? So it doesn't even let it compile. It's not really an error, but the compiler, a C compiler will let you do this. A Java compiler says, that's really stupid. You really shouldn't be doing that. So we're not going to let you compile the program because there's what's called unreachable or dead code after the return statement. But this would exit the thread, okay? That would exit the thread just like this brace exits the thread, okay? Now, let's look at the next version of this program. Look at version 4. I put a little sleep here before crashing the program. So what happens is the main thread is running over here. The GUI thread's running over here, but then the main thread called system exit and brought everything down. Okay, notice that I never hit this line, but the compiler doesn't realize that because its compiler doesn't know what the system exit method does. I never do get to line 22 if there was never any by printed over here. I never got to line 22, but I had the main thread running in a sleep mode while the GUI was running for a little while. Okay. Okay, now let's look at another version of this program. One last thing. In this picture, I show that there's a list of event handlers. So in this program, I put 2 event handlers into the list. One prints ouch and one prints ouch, ouch. Okay, so I want you to see that there could be more than one item in this list. So the the event dispatch thread will go down this list and call that method, then go call that method in the other. Okay, so there are two event handlers in the action event handler list. So you can just run this, and you'll see that when I click this button, I get 2 lines of output, because clicking that button had the effect of when I click the button, first this one is called, then that one is called. So they're just called, actually, I don't even know what order. It might even be that the order can change every once in a while. Probably it depends on what order I put them in the list. They're probably called in the order they're in the list. So you could, you could change the order they are in the list, recompile this, run it again. Now this one should have the outputs in the opposite order. Yeah, the other one was ouch, ouch, ouch. Oh, yeah. There, see, the order switched. Okay, right. We run out of time, but see, if you think about it from this point of view of this picture, I put 2 handlers in this list. When the event object came in, you went up to the button that caused the event. You went over the event dispatch thread, went up to the object that caused the event, went over to its list. For each item in that list, it called the method in that item. So it called the method in one of them, then it called the method in another. I can have as many event handlers as I want tied to a button. Why would I do that? Usually you don't have 2 handlers tied to one button, but you might. Okay. And if you go through, these examples get a little bit trickier as they go along. Like the next one, whoops. The next one has 1 event handler for 2 buttons. What this one does is it has 2 buttons. So there's a button over here and a button over here, and they point to the same event handler. They share the event handler object, which is usually something you would probably usually not do, but I'll have 2 buttons handling the same event handler object, because I can do that. But just create 1 instance of this object and put it in each button's. See, there's button 1 and button 2. So put the same handler, and now I put a counter in the handler so you could see that it's kind of neat the way it works. 2 buttons, ouch 1, ouch 2, ouch 3. See, it's the same handler, so it continues the count. So this button calls the same handler that this button calls. They share the same handler. Okay, and then I just I'll quit here. You can go through these examples. They keep doing different things, like 2 buttons with each having their own handler. So this was 1 handler for 2 buttons, and there's 2 buttons with 2 different handlers. So you can do different varieties, and you're just manipulating this picture over here. Putting multiple event handlers in this list, or having this object shared by 2 different lists, a button over here pointing at that object and a button over here pointing at that object. Once you understand this picture, you can make sense of this code way easier than without that picture. Okay. All right. We'll do a little bit more of this on Thursday. We'll say a little. We'll finish these examples on Thursday and just see that the idea is, once you get used to this picture here, it's not that complicated, but it's weird code, because you end up with stuff that you end up writing code that you never call. Notice that we never call that method. That's why I call this a callback, because the old-fashioned word for this is you're being called back by the Java virtual machine. You wrote this code, but the Java virtual machine calls it for you. So it's called back by the Java virtual machine. So the old-fashioned term for those was callbacks. I didn't get the programmer's version of callback here. Yeah, here, callback, computer programming. Yeah. They're called callbacks. Okay, same picture here. You know, the same kind of idea here of the picture. Okay, so I'm going to quit, and we'll pick up with these examples on Thursday. Anybody got any last minute question? Anybody with a question? Okay. Then I'll stop the sharing. Do you see the pop-up? I kept this out of your way. Do you guys see this? Does anybody see this? I don't know if you see it on my desktop.
I don't see your screen.
You're not sharing screen.
Oh, I'm not sharing. Oh, as soon as I stopped sharing, I got a little pop-up from the Java update checker saying, I kept this out of your way. So it was like a pop-up was not popping up while I was sharing the desktop. That's interesting. It's weird how these GUIs, which are, I kept this out of your way, as if you were talking to some human when you're just talking to a bunch of code that was, that somebody, I think, rather inappropriately tried to make it your best, like something that sounds like your friend. Yeah. So I got a pop-up saying, I kept this out of your way. All right. So I'm going to go ahead and I'll go ahead and end the meeting and see you on Thursday. Bye.